1. We are go.
So this is the final presentation for RBE501 Group B. The purpose of our project is to simulate a custom manipulator, mobile manipulator robot using both MATLAB and ROS, as well as SIMULINK, to develop a robot to assist operators in an industrial setting.
Okay, next slide. Thanks, Ishmael. So why are we doing that project? We do have a cell that has 6 machines with 1 operator, and the operator needs to do 60 quality checks every hour. With that number of quality checks in a high volume automation environment, along with auto-tending, along with changeovers, along with changing tools and bits in the machine, the operator is definitely overloaded. And there is a requirement, there is a necessity for further robotic automation. Next slide, please. So, investigating potential solutions, there has been solutions that have been developed in the past in industrial settings where applications that seem to be very hard to automate have been automated. An example we see here is in the automotive industry, where an operator is usually using, by hand, he's installing Christmas tree clamps on a wire harness, and that robot was invented to automate that operation. It's a mobile robot, so that's one of the applications that have been done in that field in the past, along with several others. Next slide, please. In our case, we are not looking at an assembly operation, but we are looking at automating the operation that has the most time built into it. And from the example on the problem statement in our case, that is performing the quality inspection testing and doing simple machine adjustments. So what we are looking for is a robot that can do dual tasks in an efficient manner. Next slide. So the objective is to propose and validate a simulated solution for the overloaded operator through a robotic device that can take over quality inspection tasks and simple machine adjustments. And this objective we'll discuss in the paper how we are going to achieve our desired objective. Next slide. So the new contribution is a custom mobile robot that was developed specifically with a manipulator for that application. The steps taken in order to reach the design shown here on a high level are identifying and understanding the environment that the robot is going to be functioning in, simulating that environment through CAD modeling, and then simulating a robot, creating a robot in a CAD model environment that would reach all the points required to do its task without being in a singularity position, and then coming up with the design and transferring it to URDF and then putting it into MATLAB and simulating it, and also doing some simulations in ROS. So that is the beginning of what we are proposing, and that's the innovation. Now, the robot does have two end effectors. One is a parallel gripper, and another is a push button style. And both are located in a way that they don't interfere with each other in order to get the both tasks done efficiently. Next slide. So the custom design manufacturing environment has the 6 CNC machines works, and part of the new contribution as well is we were trying to use VRealm and trying to use the available software in order to that is made specifically for environment. However, that was not working very well, and the environment would not transfer properly into VRealm. So we decided to use the SolidWorks to URDF exporter and transfer the environment as if it was a robot with fixed joints in there, and that transferred very well. Then we meshed that with sim mechanics, which Alfredo is going to be discussing later. Next slide, please.
Thanks, Brantley. I'll take it from here. So in terms of the ROS development, the basic steps consisted of taking advantage of the URDF file and generating one for a mobile robot, a mobile differential wheel robot. Next, we were able to integrate that same URDF into Gazebo using some custom plugins that would allow us to properly simulate the physics that are involved with the robot. Next, launch files were created in order to run the necessary packages and display those features from the terminal. The adaptive Monte Carlo localization, or the AMCL, is an open source software package that can be easily integrated into differential wheel robots. The main challenge here was configuring the hyperparameters in order to suit the dimensions of our robot. And lastly, RTAP Map, which is another open source software that we were using to perform the SLAM operations. And so again, the main challenge here is configuring the RTAP map files in order to work seamlessly with the robot we've designed in step 1.
Thank you, Ismael. So in this next slide, we're moving to the materials and methods portion for MATLAB. With it, you utilize as Rami mentioned, the URDF imported into MATLAB, and then using the imported into SIMULINK, we generated the what you see here in the left. We generated the block model for a manipulator, or for our manipulator. Here in our design, we're using a PD controller for every joint, and the blocks by itself have the capability of providing a sensing capability as well, that we use as an input to the controller to correct any vibration caused by the movement of the different joints. Here we see in the left, we see the example of the SIMULINK diagram for the actual base, which would be the mobile robot by itself. So here we are giving a planar joint behavior in the SIMULINK environment to the robot. So it behaves so that the kinematics are transferred to the actual SIMULINK environment, and leaving the world fixed because the only thing that would be moving in there would be the robot. Here we have in the next section the environment import. As Rami mentioned, we were not able to get the environment set up in vRealm, so we had to change focus to the sim mechanics simulation software, which requires URDF imports in order to function. So here in the block on the left, we see the actual block diagram for the 6 CNC machines and the flooring and the inspection table that you see on that image. Here in the results section for the MATLAB, in order to generate a proper path, or as part of the validation, we use the rapid random tree star algorithm, which allows for sampling and looking for the best possible path towards the end goal. And also we did some path smoothing techniques using the B-spline function, as you see on the left, to give a more smooth behavior to the mobile manipulator moving from point A to point B. And also in this algorithm, we also use a cost map, which adds some clearance to every obstacle or every object that's in the environment. Therefore, your path planning will always will never make contact with the actual object or machinery in this case, because it has that extra clearance. So some challenges for this approach when we introduce or when we talk about a manufacturing environment where there's going to be people. So some challenges this approach has is the amount of processing time required to develop the best potential path towards an end coordinate, and also by avoiding any hitting any humans or any operator.
So as for the results from the ROS portion of the project, as you can see here, we have listed the transformations between each frame of the robot that was generated in the URDF file. ROS does a good job of keeping track of those transforms and publishing that information to different packages that may rely on a thorough understanding of how the robot is connected. Furthermore, the robot is now also able to generate particles. It generates, right now it's configured for about 50 particles, and those particles are distributed around the robot, and the robot will attempt to determine based on the desired pose, it will attempt to determine its pose relative to the desired pose, and it's a iterative process to continue to reduce the error down to 0. The the robot is also able to be teleoperated due to a open source teleop package that is specifically designed for differential wheel kinematics. The purpose, well, the main benefit of having a package like that would be to allow an operator to manually map an environment as opposed to relying on a robot that would do it on its own, where more errors could be introduced. Also, the robot takes advantage of MoveBase, which is another open source software package, and as well as the navigation stack, which allows the robot to plan paths based on the desired endpoint that the user specifies. All of these features are located inside of separate packages inside of the robot, and they can all be ran from a terminal using Linux.
Thanks, Ishmael. So the results of the CAD modeling and image processing, after the CAD model was developed, it was tested in the environment in the different poses that the robot will need to be at. And visually, it was determined that none of these poses offer one of the common singularity positions. So that was good to ensure that we are not in any singularity situation. Also, the both environments and robot files were imported successfully to Simulink, as mentioned by Alfredo. So the URDF files transported very well, and we verified that by looking at the environment and seeing the dimensions of it and comparing the environment and relations between the obstacles in that environment to the original dimensions that were transported, that were created originally in the 3D CAD software, and both dimensions matched. So that showed that the environment transported very well in there. With that, we go to the next slide. And that is our final concluding slide. So the main goals of the project that we identified in the objective section have been achieved and verified through use of different simulation software. The main challenges in the project were related to the image processing, and through trial and error and through trying different packages, we were able to find what is most suitable for our application and optimize it. The tool used for running the final simulation is SimMechanics, which has been successful in simulating the environment. And the project shows potential for being used in as intended with custom design manipulator. However, there are several layers of testing. Definitely, this is a very involved project, and we touched on the simulation, we touched on the CAD software, we touched on the custom robot, we touched on ROS, but there needs to be much more simulation involved there, because when a robot like this is going to be used in an environment where there is going to be a lot of capital investment, simulation is very useful and a very powerful technique, because it allows the stakeholders to have their say into it. It allows people to, the designers, to actually go through the project once and simulate it several times until they have done their due diligence in the planning. So when it comes to the real thing, it is implemented with much less errors. Additional progress on the SLAM, or real-time verification collision avoidance, is required to continue perform further studies and integration between virtual environments, additional to ROS. And finally, I would like to add that additional work also on vision processing in MATLAB would definitely be required as well. SIMULINK, thank you for your time and listening, and have a good day.